So hello and welcome back. So after having looked at generalities of Lie groups and the algebras, we now return to the example that we started out doing, and that is going to be SU2 again. Okay. So again, let me remind you of what is. Yeah. Okay. Let me again start off by sharing screen. So let me remind you of what we did with SU2, and we look. So we said that this was the first. I mean, the first non-trivial uh, Lie algebra. So that, I mean, generators take this form where epsilon ABC, the structure. I mean, the structure constants, epsilon ABC are well, the structure constants are epsilon ABCs. Okay. That means that your structure constants are this, take a certain form, and this defines what the algebra is going to be. Okay. Um, all right. So then we went on to trying to understand how to construct representations of the algebra. And we said that there is, so what we are going to be doing is that we are going to be looking at the Casimir, quadratic Casimir, and that is going to help us actually, in our labeling of the what the states in the representation would be. So what we have is a two-dimensional, a representation of the algebra in a two-dimensional Hilbert space. This is going to be called two, if you wish, and for this particular thing, we also saw that t plus minus was equal to 0, t squared equal to 0. This was specific to the representation and not to the algebra. So now what we wanted to do is we wanted to construct irreducible representations, and we reverted back to quantum mechanics, and told you that the states labeled states are going to be labeled by the eigenvalues of a maximal number of commuting operators. In this case, we are going to take C2, and we are going to take one of the TAs. So this is if you wish the total angular momentum and the angular momentum along the z direction. And the algebra would be represented by eigenstates of these operators. Now we went about trying to look at it in some way. So we are saying that C2 is positive definite. So since C2 is equal to TS squared plus T1 squared plus T2 squared plus T3 squared, and everything is positive, if you fix a value of C2, then the spectrum of any of the TAs has to be bounded by that. Okay. Now let's look at states which are labeled by C and M, where C is going to be what the eigenvalue of C2 is, and M is going to be the eigenvalue of T3. And we went about trying to, construct the representation in a certain way. We said that T plus, as we know, is going to raise the M value, is going to keep C the same, and we will determine this D plus M later. So what is going to be happening is that T plus is going to generate states with eigenvalues m plus 1, m plus 2, and so on and so forth. But we come back to the fact that T3, the spectrum of T3 is bounded. So this sequence has to stop somewhere, and this sequence stops with some maximum value of m, which we will call J. So you can't go further up with this. This is what is called the highest weight state, and T plus acting on this is going to be equal to 0. So T3 again is going to give you this J eigenvalue. So that's great. Okay. Now what you can do is you can figure out just by the algebra what this, I mean C2, what exactly the C is, which links up to J. So and you can find that C is actually J into J plus 1. So that was one thing. And similarly, we can lower things by t minus. And again, if the spectrum has to be bounded from below. And this yields a lowest weight state. And this lowest weight state, again, we can call this k. And we, since the value of C2 stays the same, this has to be j. So it has to be j into j plus 1. So yeah, we can just say this is j. And we also find k. Okay, so we're going to find k. um, so k is the one that is the eigenvalue, is the is the t3 eigenvalue of the state. And you can find a relation between k and so the C2 on this k has to be, on this state has to be k into k minus 1. So what we get at the end of the day is k into k minus 1 is j into j plus 1, because both the C2 eigenvalues have to be the same. So now what we find that k can have two values, either k is j plus 1 or k is minus j. So k is j plus 1 is something that is ruled out, because we have already started with the assumption this k is less than j. So what we have is k is minus j. So any SU2 representation which is irreducible contains these two j plus 1 states with the T3 eigenvalue ranging from minus j to plus j in integer steps. Okay, so that is something that you guys knew from before. Just we have just said this again. J is called the total angular momentum, as we were saying, and 2j is also, mathematicians call this the Dinkin label. We will speak about Dinkin labels a little later on in the course. But it should be clear that SU2 now has infinite number of irreducible representations, one for each integral value of 2j. Okay, so j equal to 0 is the trivial representation, j equal to half is a spinorial representation, j equal to 1 is a vector representation. You can find out what the d plus minuses are. And you need to also remember that 2j is integral, not j, but 2j. So you can start off with this highest weight state, and repeated actions of t minus must reach you to this lowest weight states. And if there are L such steps, in that case 2j is equal to L. Okay, so this j has to be an integral, 2j has to be an integer. As you can see, it has to go in some number of discrete steps. Very good. And you can further try and represent these SU2s in terms of 2j plus 1 cross 2j plus 1 matrices. This is what we also showed you last time around. And so you can define, if you wish, the spin j representation of SU2 by a matrix which takes this form. Okay, so yeah, so I this is something that should be familiar to you from quantum mechanics. If it is not, it's good for you to go through this once again. One of the very nice, one of this very important things is, if you're looking at the j equal to half representations as a spin half, there's a spin half representation, these t's actually become Pauli matrices, half times them. The spin half representation is sort of like the simplest representation of SU2. It's also the defining representation, and it's also responsible for the name SU2. Okay, so special unitary two-dimensional things. So that's what you need to keep in mind. So let's go ahead with this a little bit more, and let's just remind ourselves that if you were to exponentiate these guys, if you were to exponentiate the spin half generators, we're going to get the representation for the finite group, which is going to give things of the form the I alpha dot sigma. This, as you know, again, this is something that should be familiar to you, is the most general 2 cross 2 unitary matrices with determinant 1. Again, if this is not familiar to you, I suggest that you try to clarify this. You can you can there's a way to show that this is the most I mean general 2 cross 2 um, unitary matrices with determinant 1 that you can actually do. So you can construct other irreducible representations in the same way. And so the spin half one is going to look like this. Okay, spin half one. Sorry, the spin one representation will look like that. Very good. So that was that. Now let's try and understand this a little bit more and try and see what we can understand, what we can get from here. So what we are going to do here in this part of the lecture is that we are going to build representations by taking direct product of the smallest representation, that is this 2, and we are so what let's see how to do this. Okay, so as I write here, let's clone the Lie algebra. Okay, so let's have two identical things that we call T1A and T2A satisfy the same algebra. So T1A and T2A satisfy the same algebra, but T1 and T2 are going to commute amongst themselves. Okay. Each of this then it's going to act on its own Hilbert space now with things which are marked with 1 and with 2, and so the sum of these guys is going to act on the product states of the form 1 and 2. Okay, so this is, if you wish, just the addition of angular momentum. Let's see how to do this. Okay, let's look at the direct product of two arbitrary representations. Let's call let's say one of this is 2j plus 1 and the other is 2k plus 1, and the highest weight states is going to be state which is a sort of direct product again, and this is going to be labeled only with the T3 T3 eigenvalue. As you saw, right, these are actually, if you call them J and M, these are actually related to each other. So let's call them J, and let's call this K. So J of 1 and K of 2. So you have to keep in mind that T3 acting on J of 1 and K of 2 is T1 plus T3 of 1 plus T3 of 2. So what happens is this becomes J plus K, if you wish. Okay. Similarly, you would have, if you act T plus on this, since this is the highest weight state, again, this again breaks into T plus 1 and T plus 2. So T plus 1 is going to act on the 1, act on J1, and T plus 2 is going to act on, K2. So what is going to happen is that, individually these are going to give you 0. So the highest weight state again is the T plus acting on the whole thing. Okay, very good. So this must be the highest weight of the two J plus K plus 1 dimensional representation. As you can see, what is happening is that this has J plus K, right? So in order to, so this is the highest weight. So we have got the highest weight state. Now let's do what? Let's try to get the rest of the states from here. Okay. So what we will do is we are going to apply some of these two lowering operators and see what it gives us. Okay. So let's see what T minus does. So T minus is going to give you something. Let's ignore the numbers from now on. So so this is going to give you some J minus 1 and K2, where this T minus of 1 acts on this, and there is going to be a J1 and K K minus 1 of 2. Okay. Now we can form its, orthogonal combination, which is, the sign will be flipped, on which, if you act this T3, this is going to be J plus K minus 1. Okay. And we can find that this is actually annihilated by T plus. So this is then what is happening is this is just then a highest weight representation of another highest weight of another representation, where the highest weight is now J plus K minus 1 plus 1. Okay. 2J plus K minus 1 plus 1. So what have we done? Just to repeat ourselves once more. So we had this highest weight state. So what we did is, we took the highest weight state of one, and we took the highest weight state of 2, and we sort of tensored them together, and then we acted with T3 on this. So T3 on this was T3 1 plus T3 2, and that gave us J plus K. Okay. We then acted with a T plus on this, where the T plus can again be broken up into T plus 1 and T plus 2. Each of these will act on, so T plus 1 will act on J1 to give you a 0. T plus 2 will act on K2 to give you a 0. So the whole state is the T2 acting on T plus acting on this whole state thus gives you a 0. Okay. So let me just clarify this once and for all. So T plus acting on J1 K2 is, as I said, T1 plus T2 plus acting on J1 K2. Now this is T1 plus acting on J1 K2 of K2 plus T2 plus acting on J1 K2. Now T1 acts only on the 1. Okay, it does not do anything on the 2. So this is going to give you 0, because T1 acting on J1, T1 plus acting on J1 is equal to 0. And this is individually going to give you 0 because T2 plus acting on K2 is now equal to 0. Okay. So that means that the whole thing gives you 0. With that clarified, now moving on. So you see that this, what has happened is that you have something where the T3 gives you J plus K, and T plus acting on this gives you 0. So this is the highest weight state, and the highest weight of this state, this is a highest weight state, and the m value of it is J plus K. So as we saw, right, so we saw that the total angular momentum was, if you call it J, then it was C2 would have been J into J plus 1, right? So if there's a J dimensional representation, this particular eigenvalue is going to be J into J plus 1. So that is now in, and we saw that if in this case it was a 2J plus 1 dimensional representation, because those were the number of states that were there, from the highest weight of that to the lowest of weight of that, there were 2J plus 1 states. Now here what we have is J has been replaced by J plus K. Okay, if J has been replaced by J plus K, the highest weight, so the representation that we are going to be now this product thing is going to give us, sorry, let me just get rid of this. The product is going to give us a representation, which is 2j plus k plus 1. Now in this representation, in this dimensional representation, what we are going to do is we have found the highest weight state, which is just this guy. Now we want to find all the states. So what we are doing is we are acting with it with this. We are acting t minus on this. If we do this, if we just drop what the numbers are in front, then it is going to lower this ones and it's going to lower this one. So it has to be some j minus 1 k and j of k, I mean k minus 1. Now suppose we look at its orthogonal state. So that just means that the sign here will be flipped. Then if we act t3 on this state, then what we are going to get is this is going to be j plus k minus 1. We will also find, interestingly, that this is actually annihilated by t plus. So being annihilated by t plus means that it is again a highest weight state, but the t3 eigenvalue has changed, right? So this has to be a highest weight of another representation, with the highest weight now with this highest weight, with this, I mean the dimensionality of that representation is going to be 2j plus k minus 1 plus 1. So this is the equivalent of the j now. Okay, hopefully that is clear. Okay, so now we are going to find more states. We can repeat this process and find new states, then now which are in the linear combination. Now you're going to lower these again, right? So if you're going to lower these, there's going to be a j minus 2 there and k. There's going to be a j minus 1, k minus 1. There's going to be a j and k minus 2. Okay, again these two two linear combinations are going to be this, they would be lowest weight states of two representations, 2j plus k plus 1 and 2j plus k minus 1 plus 1. And the third one is going to be the highest weight of a new representation where and you can see that this is going to be j plus k minus 2. Okay, so we can go on doing this, repeating at each level, until what we are going to find is that we're going to find one new representation at each level until we run out of the states and hit the lower bound of the the original representation that we had started out with. So if you have something like 2j plus 1, tensored with 2k plus 1, like we were trying to do. So this is going to break up into something. This is going to be a representation of 2j plus k plus 1, 2j plus k minus 1 plus 1, and you would go all the way down to 2 of j minus k plus 1. Okay, so that is what is going to happen. I understand that this may be a little the most general case out here may be a little hard to see, but we can actually do this, and we can do this at each level, and I would urge you to go and just work this out. So what is going to happen is that we would be able to take product of lower dimensional representations, and we can build all the other representations of the algebra. So let's do an example. Okay, let's look at spin ups. So spin ups, this is half 1 and half 2. Okay, so let's look at t minus acting on this. So t minus is going to flip one sign here and one more sign here. Okay, so this is going to, so t minus is going to split into t minus of 1 and t minus of 2. The t minus of 1 is going to flip this spin here. T minus of 2 is going to flip this spin here. Okay, so what is this? This is going to be half minus half, if you wish. That's this this state. So and so half minus half and half half of 2. This one, the half half stays as it is, and this becomes half and minus half. Remember that this is what we call C, and this is what we call M. So just keep that in mind. So then what we do is if we do this one more time, then what is already a minus can't flip once more, so this one has to flip, and this one has to flip, and again what is already up can't flip, so this has to flip. So what you get is that you're going to get a state like this. Okay, so this is going to be half minus half, half minus half of both guys. Okay, you can't lower this more, so we are done. So what have we got? So we have these three states form a three-dimensional representation of the algebra. So the direct product of the Hilbert space has 4 states, and the fourth state is the orthogonal linear combination of the thing we wrote down out here. So this was one combination. There's an orthogonal linear combination which looks like this. This, if you look at this, this is going to be killed by lowering, or this if you act with the lowering operator, that's going to be 0. If you act with the raising operator, this is going to be a 0. So this is going to be a singlet state. Okay, so what is going to happen is that if you take 2 spin halves and they are going to go into a spin 1 combination which has these 3 states, or anti-symmetrically, so that is going to be the symmetric guy. And if you were to look at the anti-symmetric combination, that is going to go into something which is spin 0. So we can we also denote this as 2 cross 2 going to 3 plus 1, indicating what the the dimensionality of the representations are. So these were two states each. This has 3 states and this has 1. Okay, so that was one thing. You can now look at more involved things. Let's suppose we look at something which is the product of a spin half with a spin 1. Okay, so this is a sort of unique highest weight state which we call 3 halves. That is a direct product of a half half with a 1 1. So if we do this, then what is going to happen is that we need the action of the lowering operators on the j equal to half and j equal to 1. So what does j equal to half do? So I'll just write these things down for you. So t minus on half and half gives you this 1 over square root of 2 half and minus half here. And t minus of 1 1 first gives you 1 0. Then you act on it with t minus once more. It gives you 1 and minus 1. So now let's look at the action of this. So let's take this unique highest weight state and act with t minus on both sides. Okay, so if you do this, then you get a root over 3 by 2 in front, and this eigenvalue is going to get lowered, right? So that now what you do on the other side is that you look at the action of t minus. You break this up into t minus of 1 plus t minus of 2. The first one acts on this half, makes it half minus half, gives this sort of 1 over square root of 2 in front. This stays the same. And my charge is gone. Give me a second. So as you can see, then you know, so yeah, I need my pointer, so give me a second again. So yeah, so you have half and half. So this as you can see is t minus has acted on this to give you this guy. So now what you have is three halves and 1 here. Once you take this root over 3 over 2 on this side, then it gives you a combination of these states. All right, very good. Now what you can do is you can now then find out what the next state in this game is, and you'll find that this is in a similar way, just a form like this. And then if you do this one more time and reach the lowest weight state out here, you are going to find that this is sort of the unique state, this, which is again what you had expected, which was half and minus half and 1 and minus 1, which were individually the lowest weight states that you of the spin half and the spin 0. The remaining states are going to be the ones which are orthogonal to these. Okay, so you have one of the states which is here, and there's another state which is here, and you have to find out what the orthogonal guys to these are. So you remember that you need to take, you need to, so if a state, so you take psi, and there is psi, sorry. So you need to just do psi. So let's say phi and psi, this is equal to 0. So you have to sort of, just implement this to see what the factors in front are. Okay, it's obvious that it's going to be the same, same sort of linear combinations as the ones you have had above, but the numbers are actually going to change. So you need to be a little careful with the numbers, and then you will see what you should get. Very good. So you will find that the orthogonal states in this one and this one. One can apply t plus on the first one and check that it is. It is going to be going to give you a 0. It's going to be annihilated. So this is the highest weight state of the spin half, spin half representations, and this is what you're going to find. Okay, so these are going to be the highest weight. So this is the highest weight state of the spin half representation. So what you find is in a nice way, what you get at the end of the day is you had started off with the spin 1 and spin half and the spin 1. So that's the 2-dimensional representation crossed with the 3-dimensional representation. And what we have found is something which is which is actually so this guy has 4 states. And so what you have is 3 halves. So one state here, one state here, one state here, one state here, and one state here. So that is a 4-dimensional representation. So that's 4, and you have also found a spin 2. Spin half here at the end of the day. So that's 2. So what you have is you have shown that 2 cross 3 is 4 plus 2. Okay, at the end of the day, you are saying how to split up 6, but it's nice to see what exactly the way these things break down into. So you take, what you do is you tensor two representations. One is a two-dimensional representation, one is a three-dimensional representation. You find a higher dimensional representation, the 4, and you also find a 2 with that. Okay, so this hopefully was an instructive class, and I would urge you to look at more things like this, and there will be for sure there when I give you some homework. But I hope that this way of trying to deal with product of representations which are SU2 representations is clarified now. This should be a reasonably straightforward. It is you have to work out the details, but the general idea with these two examples should be clear to you. Okay, so that's it for this class, and let's again speak very soon about the next class. So that's what we had for now, and let me stop sharing screen. And so until next time then.